Okay, hello everyone. So this is Module 5, Microsoft Azure AI Fundamentals, Generative AI. And remember, this is AI 900. That's the code for this course. The agenda here is fundamentals, generative AI, fundamentals of Azure OpenAI service, and we'll explore responsible generative AI. Can you hear? Am I audible? Please confirm that I'm audible. And
Yes,
that you
ma'am.
can see my
Yes,
screen.
ma'am.
Yeah? Okay.
Yes,
great.
ma'am.
Great. So the learning objectives here, after completing this module, you'll be able to describe generative AI and describe the capabilities of large language models, understand how to use Azure OpenAI to create generative AI solutions. Okay, fundamentals of generative AI. What is generative AI? AI, we've been going through this, that's, we know that imitates human behavior by using machine learning to interact with the environment and execute tasks without explicit direction on what to output. Yeah. AI imitates human behavior and using machine learning. Gone through this. Yeah. And generative AI creates original content, such as generative AI that has been built into chat application. Generative AI applications taking natural language input and return appropriate responses in a variety of formats. Yeah, generative AI. Remember, it creates original content, such as generative AI that has been built into chat applications. You have natural language, you have image generation, you have code generation. Okay, I'm going to break it down somewhere. So I'm going to go through some, going to detail it a bit. Yeah. Okay, so fundamentals of generative AI. In this module, you will explore the way in which large language models. So when you hear LLM, that's large language models, enable AI applications and services to generate original content based on natural language input. LLM. You'll also learn how generative AI enables the creation of AI-powered copilots that can assist humans in creative tasks. We've come across copilots. Can somebody tell us what's copilot? What does copilot do? What do you understand by copilot? Somebody can unmute and speak. Copilots. Oh, you haven't come across copilot? No. Anybody?
Copilot.
Yeah, go
Copilot
on.
is the AI assistant that comes with Microsoft Edge. It's the AI assistant that comes with Microsoft Edge.
Say that again.
It's the AI assistant that comes with the Microsoft Edge.
Okay. Yeah, AI assistant that comes with Microsoft Edge. Yeah. Any more? What's Copilot?
Copilot is more like an artificial intelligence software that helps humans in carrying out their tasks, making them more efficient and effective in carrying out responsibilities.
Yeah, now in Microsoft suites, you have Copilots. Yeah, you have Copilots in Word, Excel, PowerPoint, name it. Yeah, remember it's Copilots. You are the pilots. Yeah, it just assists you. That's why it's called co-pilots. Yeah, you are the pilots. So by the end of this section, you'll be able to do this, understand generative AI's place, the development of artificial intelligence, understand large language models and their role in intelligent applications. Yeah. Remember, we mentioned generative AI, large language models, LLMs. Describe how Azure OpenAI supports intelligent application creation, and describe examples of co-pilots and good prompts. I'm sure you've all come across prompts. You know what prompts is. Yeah. Okay. Let's look at image generation. Some generative AI applications can interpret a natural language request and generate an appropriate image. For example, you might submit a request like create an image of an elephant eating a burger. Yeah, that's a prompt. Image generation, and it will generate that image of an elephant eating a burger. Yeah, so once you give it the prompt, generates the image for you. And code generation, here you have some generative AI applications are designed to help software developers write codes. For example, you could submit a request like, show me how to code a game of tic-tac-toe with Python. And it generates the codes for you. Yeah? So it makes life a lot easier for developers. Yeah. So it doesn't mean that developers don't learn how to code anymore. It just assists them writing code. So that's code generation. Even if you're learning Python, you could also use such to learn how to write codes. Okay. It's code generation. I have the large language models, transformer model, the LLM. So don't dwell too much on the details of the model architecture. The key points are on the slide, yes. Also, the next few slides will explore some of the main concepts in detail. I'm going to look at the slides now. Machine learning models for natural language processing have evolved over many years. Okay, let's look at okay, here we have large language model. Okay. Yeah, generative AI applications are powered by large language models, LLMs, which are a specialized type of machine learning model that can use to perform natural language processing. You remember what you mean by NL, natural language processing? Okay. From natural language processing tasks, including determining sentiment, otherwise classifying natural language text. So this is they're used to perform natural language processing tasks, including summarizing text to comparing multiple text sources for semantic similarity, generating new natural language. Yeah. What's natural language? What do you understand by natural language? Can somebody unmute and tell us? Tell us
Natural
what
language
yeah, go on.
is a feature of AI that deals with generation of spoken or interpreting of spoken or written text.
Okay. Languages that you understand, like English, Spanish, generating new natural language. Yeah. A language that everyone can understand. So you have the large language models, transformer model. Yeah. So transformer model architecture consists of two main components or blocks. You have the encoder, and you have the decoder. So an encoder block that creates semantic representation of the training vocabulary. Encoder creates semantic representation of training vocabulary. And the decoder block that generates new language sequences. Decoder. Or you can even see here the diagram. Features and widths, embeddings. So this is the encoder. Feed forward, tension, feed forward, tension. They have the positional encoder, embeddings, organization, inputs. Yeah, and this is the coder here. So that's the output here. The input text here. Okay. You have a feed forward here. Shown. So these features and rich embeddings. You have the positional coding, the input here. Coder, and that's the output. So text is tokenized, so each word or phrase is represented by a unique numeric token. This is where you do the tokenization. So the tokens are signed embeddings. You can see that you have the embeddings. So once you have the inputs, you have your inputs there. Then the tokenization. The tokens are signed embeddings. A vector value in multiple dimensions. And attention layers examine each token in turn and determine embedding values that reflect semantic relationships between tokens. Then the decoder, these relationships are used to predict most probable sequence of tokens. Because after here, features and risk embeddings, then it takes it to the encoder. Where you get an output. So that's your large language models transfer. Okay, let me go back to
Sorry, excuse me, ma.
yeah.
I'm not sure I understood that last large language model you're explaining about the encoder and decoder. I'm not sure I get what you're trying to say.
Did you understand the encoder and the decoder?
No.
So let me go back. Okay, I'll go through it again. I said the large language models, the transformer model. Yeah. Yeah, I did explain that the transformer model consists of two main properties blocks, the encoder and the decoder. Just like you have the diagram here. Yeah? You have the encoder and the decoder. So once you have the inputs, yeah, the inputs, you have the encoder block, yeah, creates semantic representations of the training vocabulary, while the decoder block, yeah, generates new language sequences. And so if you have the input text, you can see that at the bottom here. You can, once you have the input text here, yeah. So the text is tokenized. So each word or phrase is represented by a unique numeric token. Yeah. So we're going to go through the tokens in the next slide. Yeah, we'll see what the tokens does. Yeah. But I just understand that the text is tokenized. So each word, remember, you are inputting in text. Yeah. So each word or phrase is represented by a unique numeric token. Yeah. And the steps, the tokens are assigned embeddings. Yeah. These are vector values with multiple dimensions. The next slide will explain it better to you. Yeah. So attention layer examine each token in turn and determine embedding values that reflects semantic relationships between tokens. Yeah, and in the decoder, these relationships are used to predict the most probable sequence of tokens. Yeah, the next slide will explain what the tokenization is. Yeah, I'm going to explain it here. So let's wait for this. Sure you understand it, but once we go through that slide. Okay. Okay. Let's look at this. Let me go through this. Okay, today's cutting edge large language models, LLM, are based on the transformer architecture, just like we saw, which builds on and extends some techniques that have been proven successful in modeling vocabulary to support NLP. What's NLP again? NLP terms. Who remembers what NLP is?
Natural language processing.
Natural language processing time. Yeah. And in particular, generating language. Okay. And transformer models are trained with large volumes of text, enabling them to represent the semantic relationships between words and use those relationships to determine probable sequences of text that make sense. Transformer models with large enough vocabulary are capable of generating language responses that are tough to distinguish from human responses. Yeah. Okay, I'm going to let me go back to this. So, okay, let's go back to this and see. Okay. So here, large language models tokenization. Step one, that's the tokenization. So the first step in training a transformer model is to decompose the training text into tokens. Yeah. So example sentences. I heard dog bark loudly at a rat. So I here represent I with numeric, remember, with 1, heard 2, A 3, dog 4, bark 5, loudly 6. So each word is represented with a numeral, at 7, and cat 8. Yeah, you already have A as 3 there. So please note that. Yeah. So the sentence is now represented with the tokens 1, 2, 3, 4, 5, 6, 7, 3, 8, because A is already 3. You can see that on the screen. So note A is tokenized as 3 only once. Similarly, the sentence I heard a cat would be represented with the tokens I 1, heard 2, A 3, cat 8. That's 1, 2, 3. So do we understand the tokenization we're talking about? Are we following?
Yes,
Hello.
Yes, ma'am.
Yes, ma'am.
Okay. So that's the tokenization that is explained right now. Okay. Let me go back to this. So in practice, the specific implementation of the architecture vary. For example, the bidirectional encoder representation from transformers, that's BERT, bidirectional. representation. BERT stands for bidirectional encoder representation from transformer. BERT model developed by Google to support the search engine uses only the encoder block, while the generative pre-trained transformer. So please take note that GPT stands for generative pre-trained transformer. You have ChatGPT, you have so model developed by OpenAI uses only the decoder block. Okay, let's go back to this. Yeah. Let's look at step 2 here. Large language models, they embedded. Remember, in the previous one, we discussed the tokenization. So here, we're going to look at the embeddings, just as we saw on this chart. Remember here, this is the tokenization, and this is the embedding. So we're going through what we have on the chart here. So the embedding, step 2 is the embeddings. So the relationships between tokens are captured as vectors, known as embeddings. Relationship between tokens are captured as vectors, known as embeddings. So here we have 10. Okay, here we have 10. Skateboard 331. Yeah, embedding. 4 is dog. 8 is car. Remember where we did the tokenization? Yeah, it's got 8 cards. Yeah, if we go back there, 5 is back. That's the embedding with the. Let's look at the explanation. But before we do this, okay, here, let's look at, while a complete explanation of every aspect of transformer model is beyond the scope of this model, an explanation of some of the key elements of transformer can help you get a sense of how they support generative AI. Yeah. I hope you're all going through your learning path. Yeah, because on your learning path, all these are explained very well too. Yeah, so if there's anything you don't really understand, you can go back there and go through it again, the learning path. Okay. Okay, so let's go through the large language models tokenization here. I'm just going to throw more light on it. So the first step in training a transformer model is to decompose the training text into tokens, like I mentioned earlier. In other words, identify each unique text value. That's where you assign the text a numeric value. Remember the example we went through. Yeah, are we following?
Yes, ma'am.
Okay. Okay, for the sake of simplicity, you can think of each distinct word, the training text, as a token.
Yes, ma'am.
Yeah, or in numeric. Though in reality, tokens can be generated for partial word or combination of words and punctuation. Okay, like we did, what we did was we assigned each word a figure. Yeah. As you continue to train the model, each new token in the training text is added to the vocabulary, the appropriate token IDs. So I is 1, like we saw, head is 2, A is 3, dog is 4. With a sufficiently large set of training text, a vocabulary of many thousands of tokens will be compiled. So you give them each word a figure. Yeah? And the large language models embedding, yeah, while it may be convenient to represent tokens as simple IDs, essentially creating an index for all the words in the vocabulary. They don't tell us anything about the meaning of the words or the relationship between them. We are just assigning these words, figures, tokens. So to create a vocabulary that encapsulates semantic relationships between the tokens, we define conceptual vectors known as embeddings for them. So we're going through embeddings. We've seen what tokens are, just assigning figures to these words. So vectors are multi-valued numeric representations of information. For example, 1031, in which each numeric element represents a particular attribute of the information. Yeah, for language tokens, each element of a token vector represents some semantic attributes of the token. Yeah, so each figure represents word. So the specific categories for the elements of the vectors in a language model are determined during training based on how commonly words are used together or in similar context. Like we saw that A appeared twice. The sentence, so we're looking at is the same figure. Yeah. Once you assign a word, a figure, and it stays. So it can be useful to think of the elements in a token embedding vector as coordinates in multidimensional space, so that each token occupies a specific location. Yeah. The closer tokens are to one another along a particular dimension. So the more semantically related they are, in other words, related words are grouped closer together. Related words are grouped closer together. So the locations of the tokens in the embedding space include some information about how closely the tokens are related to one another. Yeah. In the previous example, we looked at the sentence. Now imagine the sentence is part of a whole book of text. We have tokenized all the text. Now we map the relationship between tokens based on what tokens they often appear next to. Just note that, the tokens, once you give them the figures, you represent each word with a figure. Yeah? I saw the example. So for example, the token for dog is close to cat and also to back. The tokens for cat and back are close to new. Yeah, so you have tokens for each word. Yeah, the token for skateboard is farther away from the other tokens. So once you give a number, just take note of it. That's what this is explaining. Let's go back to that and see. Okay. Yeah. Remember, okay, if we go back to this, remember that dog is 4, bat is 5, cat is 8. So once you know the tokens, sign them. Okay, here, token here. Okay, skate is 10 here. Let me see that skate is 10. Dog is 4 with 4. Cat is 8. Token for cat is 8. Yeah. New here is 9. 9, you can see that. It's 9. So once you assign the token, you know what word you assign it to. Okay, let's see. Let's go back to this. Okay, note, so the previous example shows a simple example model in which each embedding has only 3 dimensions. Yeah? Real language models have many more dimensions. There are multiple ways you can calculate appropriate embedding.
Oh, good.
Sorry? Please, can you mute yourself if you're speaking? Somebody has a voice about. There are multiple ways you can calculate appropriate embeddings for a given set of tokens, including language modeling algorithms like what2vec or the order block and transformer. Okay, let's go back to this. Okay. Okay, here we have large language models attention. So this is step 3. We have step 3 attention. Capture the strength of relationships between tokens using the attention technique. Example, predict token after dog. Token after dog. Represent ahead of dog as vectors. Okay. Here you see ahead a dog back. Assign herd and dog points. So these are examples. And several possible tokens can come after dog. Most probable token is added to the sequence, in this case, back. Okay, let's look at the explanation of this. Okay. So the large language models attention. Yeah. So the encoder and decoder blocks, the transformer model include multiple layers that form the neural network for the model. We don't need to go into the details of all these layers, but it's useful to consider one of the types of layers that is used in both blocks, the attention layer. Okay. So attention is a technique used to examine a sequence of text tokens, try to quantify the string of the relationships between them. So it's used to quantify the strength of the relationship between them. But in particular, self-attention involves considering how other tokens around one particular token influence that token's meaning.
Sorry, ma'am.
Yeah.
Yes, please. What slide are you sharing?
What slide am I sharing?
Yes, I don't know. What I've been hearing, I don't know whether it's a problem from my end, but it has not been correlating with the slides I've been seeing. Like this, not right now. I'm seeing large language models, attention, step 3, attention, capture the strength of relationships, an example, goal, represent, assign, and a diagram at the side.
Is that what you can see now?
Yes, that's what I can see now.
So what can you guys see now on the screen?
Currently seeing
Okay.
what you're just talking about. I think the issue is from his end. Maybe he'll leave and come
What's
back.
going on now? It looks like it's dragging. I can't. Yeah, what you're saying is that your internet? Is it Okay, what can you see on your screen now?
I can't
Ma'am, I'm seeing, but I think it's from his end. It's correlating with what you're saying.
You can see what?
I can see what you're saying. Like what you're saying is correlating with the slide.
Okay.
Language
Okay, the
model.
other guy, the person that first spoke, you're seeing something different.
I can't see anything at all.
You can't see anything.
Yeah, I'm
Yes,
just
I can't see
seeing your
anything
name.
now.
Okay, if you can't see anything, if it's only you, others can see, yeah? Who else can see the slide?
I can't see anything either.
Okay, if you can't see, why don't you leave the meeting and come back in? Yeah? Who else can see the screen?
I can, ma.
Okay. Yeah, for those that cannot see, please leave the meeting and come back. Okay, please put up your hands if you can't see the screen. If you can't see the screen, please put up. Raise your hand, please, if you can't see the screen. Okay, so everybody here can see the screen. Okay. Okay, please raise up your hand if you cannot see the screen. If you can see the screen, please raise up your hand. If you can't see the screen. Only one person can see. Only two people can see the screen. 3.
Sorry, ma, is it can't or can see the screen?
Can't see. Okay, so everybody else can see the screen. Okay. So if you cannot see the screen, please leave the meeting and come back in. Thank you. Okay. So attention is a technique used to examine a sequence of text tokens and try to quantify the strength of the relationship between them. In particular, self-attention involves considering how other tokens around one particular token influence that token's meaning. Yeah. So what I could do now is let's go back here. Okay, yeah, let's look at the coder and decoder. So okay, we looked at the encoder in the diagram and the decoder. So in an encoder block, attention is used to examine each token in context and determine an appropriate encoding for its vector embedding. The vector values are based on the relationship between the token and other tokens with which it frequently appears. Yeah, that's a vector value based on the relationships between the token and the other token in which it frequently appears. So this contextualized approach means that the same word might have multiple embeddings depending on the context in which it is used. For example, the back of a tree means something different to I had a dog back. In the same back? Yeah? Are we following? B-A-R-K,
Yes, ma'am.
back. Yes, the back of a tree. Yeah, it means something different. So I had a dog back. So this conceptualized approach means that the same word might have multiple embeddings, yeah, depending on the context in which it is used. So same word, yeah, different meanings. The back of a tree is different than the dog back. So in a decoder block, attention layers are used to predict the next token in a sequence. So for each token generated, the model has an attention layer that takes into account the sequence of tokens up to that point. The model considers which of the tokens are the most influential when considering what the next token should be. Okay, remember that the attention layer is working with numeric vector representation of the tokens, not the actual text. The decoder, the process starts with a sequence of token embeddings representing the text to be completed. Okay, so I'll go through this, then we'll go through let's go through the slides of the what we've been talking about. Okay, let's finish this. Come back here. So during training, the goal is to predict the vector for the final token, the sequence based on the preceding token. The attention layer assigns a numeric weight to each token, the sequence so far. It uses that value to perform a calculation on the weighted vectors that produces an attention score that can be used to calculate a possible vector for the next token. So in practice, a technique called multi-head attention uses different elements of the embeddings to calculate multiple attention scores. Neural network is then used to evaluate all possible tokens to determine the most probable token with which to continue the sequence. Never mind, like when you start the lab, when you have hands-on there, you understand the small. Okay, anyway, you all know that your tokens, you assign numbers to it. Once you know that, makes life easy. Once you know the numbers for each word, yeah, and that's where it starts. And the process continues iteratively for each token in the sequence, with the output sequence so far being used regressively as the input for the next iteration, essentially building the output to one token at a time, just like we saw in the diagram, the encoder and the decoder. So in the following animation shows a simplified representation of how this works. In reality, the calculations performed by the attention layer are more complex, but the principles can be simplified as shown. So one, we have a sequence of token embeddings. It's fed into the attention layer. Each token is represented as a vector of numeric values. Yeah. So don't overthink it. It's yeah, the goal in a decoder is to predict the next token sequence, which will also be a vector that aligns to an embedding the model vocabulary. Yeah. Just as finding time and they say that is the yeah, but the thing is once you start once you work on the lab, you get to understand that. Okay, we'll go on to copilots later, but let me just go through them before we watch. Okay, so the attention layer evaluates the sequence so far and assigns weight to each token to represent the relative influence of the next token. The weights can be used to compute a new vector for the next token with an attention score. Multi-head attention uses different elements, their embeddings to calculate multiple alternative tokens. A fully connected neural network uses the score in the calculated vectors to predict the most probable token of the entire vocabulary. And the predicted output is appended to the sequence so far, which is used as the input for the next iteration. Yeah, just as we saw in the diagram, remember that diagram. Yeah. Remember this diagram. The embeddings, tokenization embeddings. And we have this the input here, positional encoding, now the outputs. Okay. Okay, so let's look at yeah. Before we go on to do we have questions so far? What we did
No, ma.
here?
No question, ma.
Okay, I see some people have their hands up. David? David and Oluwa, you have your hands up. Do you have questions? Any questions?
No, ma, sorry, I forgot to put my hand down.
You forgot your hands up. Okay. Looking at. Okay. I think in the next class, we'll continue with copilots. Yes. The one that starts copilots. Sorry? Do we have any questions on what we've done so far?
No question, ma.
Okay. But it would be nice to also go through your learning path. So you can digest what you learned. Yeah, at this point, do we have any, is there any issue with your projects you want us to go over before we call it a day? Any issue with your projects you want us to go over as a group? Yeah? Okay. So everybody is okay with their projects. Okay, let me just let's just go through this before. Okay. During training, the actual sequence of tokens is known. Yeah. As during training, the actual sequence of tokens is known. We just mask the ones that come later in the sequence and the token position currently being considered. Yeah. Actual sequence of tokens, no. That's the actual. So as in any neural network, the predicted value for the token. Remember, you know, The actual is known. We all know that. During training, you already know the actual. Yeah? It's the predictor you don't know. Remember, it's the unknown. Yeah. Okay, so the predicted value for the total vector is compared to the actual value of the next vector sequence. Because the actual is the known one. The predicted one is just a prediction, remember the word, the predictor. And the loss is calculated. The weights are then incrementally adjusted to reduce the loss and improve the model. So that's how you train your model. You have your actual, you have the prediction, and yeah, so you calculate on to improve the model. Okay, when used for inference, predicting a new sequence of tokens, the trained attention layer applies weights that predict the most probable token and the model's vocabulary that is semantically aligned to the sequence so far. Yeah, just remember that you have the actual sequence, you have actual, yeah, you have the predictions. You train it, keep improving. Okay. So what all of this means is that a transformer model, such as GPT-4, as the model behind ChatGPT and Bing. We all know ChatGPT and Bing. Yeah, it's designed. That's its. You can see that. Yeah, the transformer model. Yeah, GPT-4 is the model behind ChatGPT and Bing. So it is designed to take in a text input called the prompt. Yeah, you all know prompts. What do you understand by prompts? Can somebody tell me what is prompt again? You can unmute and tell us what is prompt. Yeah, go on. Just tell us what do you understand by prompt? And nobody wants to speak again. Nobody wants to tell us. Okay. I'm sure you all know what prompts are. All the questions you ask ChatGPT are prompts. All the texts put in are prompts. So you generate a syntactically correct output called a completion. In effect, the magic of the model is that it has the ability to string a coherent sentence together. So this ability doesn't imply any knowledge or intelligence on the part of the model, just a large vocabulary and the ability to generate meaningful sequences of words. Yeah. So remember that GPT-4 is a transformer model. Yeah. I used to build the model behind it is GPT and Bing. What makes a large model, large language model like GPT-4 so powerful, however, is the sheer volume of data with which it has been trained. Yeah. It's like public and licensed data from the internet. GPT-4, and the complexity of the network. So this enables the model to generate completions that are based on the relationships between words, vocabulary on which the model is trained, often generating outputs that is indistinguishable from our human response to the same prompt. Yeah. So I'm sure you people have used a lot of, if not all of you, have used ChatGPT and Bing. Okay. So the next class will be we're going to starting on copilots. Copilots, what copilot means. So okay, so I will have another class on Friday. Okay, same time, 4 to 6. Hello, are we still here? Can you still hear me? Hello?
Yes, ma.
Okay.
I can
So
hear
we'll
you,
have
ma.
another class on Friday, 4 to 6. Okay. Okay. Yeah, but please finish up your projects. I'll see if I can post more projects so that at least before you resume school, you would have done almost all the projects. Okay.